Hey guys, my name's Ryan Parisian. I'm from the UBCO Aero Club. I'm out here with Jin Strawn today. We're going to be launching this 7-foot rocket to about 1,500 feet and explaining to you guys some of the physics and engineering concepts that go along with it. Most model rockets fly on the same type of flight profile. You go up, you pop open, release parachutes, and you come down. This rocket, it's a very similar concept. We just do it in two pieces. So what's going to happen is we're going to send an electrical current to these set of wires here, which will light off this motor, which we will show you guys later in another video how it's assembled. And it's going to send the rocket up at a very fast rate of acceleration and speed to about 1,500 feet. At 1,500 feet, again, you will see in the later video of the ejection charge will go off, and it will split this rocket in two, like so. And inside, there is a parachute that will be better packed in the future than this to ensure that it doesn't come down ballistically. And then there's a parachute inside this one as well. They come down in two separate pieces. We hopefully go try to find them. This is pretty much how most amateur rockets will fly. You can do a couple different things, such as putting more than just one motor in the bottom. That's called clustering. Or you can also do what's called staging, where essentially you would have two of these boosters. The first one would go off, drop off, come back to Earth, and the second one would fire and keep the rocket going even higher. But that's complicated. We're not there yet. So when setting these motor ejection times, it's really important to make sure that you set it for the right time so your rocket doesn't come down ballistically. So when these motors burn...
Oh, I went to the face shot, sorry.
When these motors burn, they'll burn from the bottom up till about this point. At this point, there is some compressed cotton that sits in here, and what we're going to do is take some gunpowder in this little tube, put it in here, and plug it off. But now, these rocket motors come with a 14-second preset burn time, but that might be a bit too long for our rocket, and we might end up having it smash back into the ground. So what we're going to do is remove some of that volume of cotton in order for the burn time once the motor is burnt out and burning the ejection charge to be less. And how we're going to do that is with a tool like this. And what you can see is that we can remove either 4 seconds on this side or 8 seconds on this side, and that corresponds with the volumetric size of the slots drilled into the aluminum.
So we're removing cotton now.
Yeah, and that should be the end of it there. We'll back it out. There we go. Right. So when putting these Aerotech high power motors together, they don't come with an ejection charge pre-installed. So we're going to do that now. First step is to put this little washer in. And the point of the washer is to make sure that the plastic doesn't just get burnt through with the cotton, and that it actually controls the amount of surface area of the gunpowder exposed to the burning charge to kind of slow it down. Next, we're going to well, I guess install is not the right term, but put the gunpowder in. Usually for these 2.6-inch diameter body tubes, they recommend about 0.5 gram. I like to put about 3/4 just to make sure, and I'm just going off the measurements there. No fancy scales or anything. And 0.5 gram always looks like a lot more than it is. Alright, here we go. Now we'll tap that out to make sure that it's flush, and then we're going to install this cap just so that it can actually generate some pressure, which is not easy in the cold.
I'm pretty sure if it didn't require significant pressure to put the cap in, it would not require significant pressure to blow the cap back out again, too.
That's a good fact.
Newton's third law.
So once the cap is flush, we're ready to install the igniter. So the next step with this motor is to install the igniter. Something's got to light it off, and it's not going to be me standing next to it with a blowtorch. So, these igniters are essentially just some very thin wire that when we pass some current through it are going to get very hot, and there's what's called a pyrogenic material on the top of it, just something that when it gets hot, it starts to burn. Gunpowder, something like that. This is kind of just...
Looks like magnesium, actually.
Yeah,
like
it's some sort of flammable material that can be coated on a surface. So with these, it's very important to make sure that the igniter goes all the way to the end of the motor. This is because if the motor starts burning from the front to the back, it's not going to generate as much pressure as if it was burning from the back to the front. Because when it's burning from the back to the front, all the fire is going out this way, so everything is going to light at once. Whereas if it has to burn this way, it's fighting its own pressure to work its flame up the channel here. And you can actually lose about half of your performance in your motor just from igniting it from the front. So the next step, another ignition little tidbit, is that rocket motors like to be pressurized when they are first lit. This is because the combustion process and the stoichiometry works better under high pressures, and that is typically why in larger rocket motors a gunpowder charge will be used to light it, but for our case this little pyrogen one is good enough. But to generate that pressure we're going to use a cap. This alone will be a little too much pressure, so we're going to poke a little hole in it. Just a hole is good enough. And then it just simply fits. Try to get this in the little slot just to make it easier on the pad. And this simply just fits over the wiring like so. It's not terribly easy, but there you go. And then you just take your wires, peel them back, strip the coating, and there you have it, a rocket motor completely ready for flight. Next step is to put the motor in the rocket. It's pretty simple. Most rockets just have a bulkhead and tube built in. Literally just like that, slides in. This goes over top.
And to be clear, putting an explosive rocket setup in your vehicle is perfectly safe. You can do this at home.
Yes, it is. Just make sure these wires don't get statically charged. They need about 12 volts and an amp, and they'll go off. So don't give it that, and you'll be okay. First couple things with a rocket, you've got three main parts. You've got your nose cone, you've got your body tube, and you've got your fins, as far as the airframe goes. They all have three really main important things. Each one of them contributes to a certain lift amount, just like an airplane wing, and we have to factor that in with where the center of gravity is in the rocket. So when calculating rocket flight stability, you'll come up with two figures. There's the center of gravity and the center of pressure. You always want your center of gravity to be in front of your center of pressure. You can tell this if you hook the rocket up to a string and swing it around, it'll fly straight. If your center of pressure is in front of your center of gravity, the air is actually actively trying to flip the rocket backwards and make it fly backwards, which is not optimal. So the way we control that is we can do a couple of things. To start, we have two main lifting forces on the rocket. Anywhere there is a curved surface, you will have a lifting force. So along the nose cone here and along the fins in the back, we will generate lifting surfaces. Because this is in the front of the rocket, we don't want lift here. Any lift or drag will cause stability, and we want stability ideally in the back because we want this thing to go forward. So what we need to do mathematically is make it so that these fins produce more lift than this nose. If we do that, then we will have a straight flying rocket, and the more we do that, the more stable it will be. We talked about stability, but now we're going to talk about overstability, which might not sound like a problem, but can actually be a really bad thing when it comes to rockets. So, what happens when we're overstable? Well, what's going to go on, usually it happens for two reasons. Either A, your fins are too big, or B, your rocket is too short for the size of fins you have. What'll happen is that your fin will be so big that when it puts this torque on the rocket to change it, the lift force from the nose and the body is not going to be enough to damp out that motion. So it's going to let's say we're starting this way and we want to come straight. The rocket, the fins, because the air is flowing this way, causing a drag on the fins, is going to push it like this. And in the ideal world, our nose now has equal air force, so it's going to be damped uniformly around this inertial moment. But what'll happen if our fins are too big is that our nose cone is not going to be able to damp it, so as soon as the rocket comes out of perfect airflow, the fin is going to catch it again, except on the other side, and it's going to swing back. And this motion is going to keep going and going and going until we inevitably have a catastrophic failure. So, we just talked about stability and why we need fins on a rocket. But fins only work when we're going fast enough for the air to be traveling over them to put a force on them. And we have no other sorts of stability for this rocket. So, how are we going to get it to fly straight when it's going slow in the beginning? The answer is this. It's called a launch rail. What it's going to do is essentially the rocket sits on it with these things called launch lugs, and the launch rail is going to give it some form of stability as the rocket accelerates to a speed where the fins can start taking effect. Most launch rails just need to be long enough for the rocket to be going about 80 kilometers an hour. That's when the fins will take effect, but if you're building a rocket, especially one that costs a lot more money, I would definitely do the math on it first. So now I'm going to show you guys how to pack the parachute in this rocket in particular, but it's pretty much the same process for any parachute. The number one thing is you want to make sure that your lines aren't tangled. Like, they look a little tangled on the bottom here, but it's not the end of the world. Again, we're dealing with a lot of various forces here, so try to keep it as best as you can, but at the end of the day, we're all human. Next step is going to be, you're going to want to fold the parachute so that it is essentially symmetrical on its lines. So you can see here that the lines are, each one kind of has its own pair. And then we're going to come through and make a triangle with it, like so. You can see the lines are still separated down there. And then we're going to fold at the tip of this triangle until we get like a decent size thing like this. It's going to vary based on the size of your parachute. Then what you're going to do is take this section here, that's not your lines, like the front section, fold it over your thumb so it's roughly equal in length. Fold this over like a taco, and then take your lines, bring them to the end of the parachute, and holding them with your finger, you're going to want to wrap it around the parachute. And then your shot cord, you're not going to wrap around the parachute. If you do, chances are it will get pretty tangled up. The shot cord is important because when the parachute deploys, we don't want all of the energy of that like slowing deceleration action to be transmitted into the body of the rocket. These things are only made of cardboard, so they're pretty easy to tear apart. So that's why we use something like this, nylon elastic shot cord to take some of the energy out of that deployment event. Same process for the bottom one here. I'm not going to pack it nicely, just in the interest of showing you guys how these parachutes go together. And of course it's stuck in there.
One eternity later.
So, as you saw towards the end of the previous video there, if we just pack this parachute in this booster and we shove this one in on top, when our ejection charge comes off, this booster is going to come out, but it's going to shove this parachute into this tube, and this one is not really going to go anywhere. So, what we do to solve for that problem is we take this top booster, or the payload section's parachute, and we put it in first. And then we take the booster parachute and put that in second. And this is absolutely not how you want to do this. You want to do this with care when you actually do it, but I'm just doing it for the sake of speed for this video. And then probably edit this out.
Well, we will now.
Faster. Okay. So, now you can see that when the parachutes come to deploy, it'll pop out like that, and then of course this one's going to keep traveling, so it's going to keep pulling on this, and then both parachutes come out nicely and effectively. And as you can see, we folded this one and it's coming apart nicely. Even just the wind can kind of open it. And this one, you're going to be hitting the ground. So make sure you pack your parachutes properly.
Nice.
So right now Ryan is carefully quantifying the wind speed and direction.
Yes. So we got some like ever so slight amount of wind from this way. So what we're going to try to do is try to point the rocket into that direction so that when it goes up, it's kind of going to fly this way, have its ejection event, and then it'll drift back, hopefully directly over us with the prevailing wind. We'll see. Usually you go hiking for these things, so we'll find out. So when you're setting up your rocket for launch, once you kind of point it into the direction you want to go, you want to make sure that the launch rod is facing away from the side that the rocket is leaning. It just makes it so that the rocket can slide nicely on it and there's not going to be a ton of friction. Whereas if we put it the other way, it might get stuck on the launch rail, give it a bit of a wobble and send it way, way downrange, and we don't want that. So. So just coming up, we found the first portion lawn darted just over there. But we got pretty lucky on the second portion because here's the tree line. And there it is there. So this is why it's really important to make sure your ejection charges are timed.